Hello, class. This is Mr. Hart. And in this podcast, we want to start the next lesson in this unit, and this is about the inverse square law. Okay. Now, this is a hugely important law in physics that applies across many parts of physics with sound and light and electricity, and all these different things have the inverse square law in them. But we're going to see it for the first time when we talk about gravity, and we want to go over what it means and why it's so hugely important and why it applies to all these different fields. Okay. So in class, we did a little lab called the gravity force lab where we looked at how the force of gravity between two objects changes depending on the distance between them. And what you should have found is that when you increase this distance, it doesn't just linearly decay, it actually decays by the square of the distance. Okay? And this is what is known as the inverse square law. Okay? So the inverse square law basically states that gravitational force spreads in relation to the square of the distance. Okay? So let's think about it this way. Let's say I just have a certain amount of gravitational force and I call it F. So I have two objects and they're such and such distance apart and they have such and such mass and it gives me this force. Okay? Well, if I suddenly double the distance between the two objects, so they have a certain gravitational force and then I double that distance between them, you might be tempted to think that then there's going to be half as much force. But it's not going to be that. It's actually going to be a fourth as much force. Okay? Because in other words, you take whatever force, and if you increase that distance by 2, you take the square of that distance, and that tells you how much force you now have. Okay? So I don't have half as much, I have a fourth as much, because 2 squared is 4. If I triple that distance between them, okay, it's not a third as much force, it's actually 3 squared as much force, right? So F over 3 squared, so it's actually a ninth the amount of force. So this is really tricky for a lot of students because they think, oh, well, if you double the distance, it should be half the force. If you triple the distance, it should be a third of the force. But you got to include that square factor, okay? And the reason this occurs by the square factor is because the force is dissipated spherically. Okay, I want you to think about that for a second. We're not spreading over 2 dimensions, right? It's not just a circle that's spreading out. It's spreading out over a sphere, right? Because we live in 3 dimensions. So that force is getting spread out over all 3 cardinal directions. And so that's going to affect how much energy or how much force you have, okay? So it's really a cool concept once you kind of solidify it in your mind, okay? And this is going to apply to sound and light, okay? Electric force, a lot of different types of forces, the energy of certain things, the way heat spreads is going to be kind of related to this. A lot of things depend on this inverse square law, okay? And again, it depends on the geometry we live in, okay? So let me do a drawing to kind of help you think about this, to kind of describe why this works and why 3 dimensions makes the inverse square law work. Okay? So let's think about the brightness of a light, okay, to think about this for a second. And let's just say we're thinking in 1 dimension for right now, just 1 dimension, okay? So if a light only travels in 1 dimension, like a laser, for example, okay, we shouldn't expect the brightness of the light to really dim. Now, lasers do spread a little bit as they travel. Okay, so this isn't completely true. But if we had a perfect laser, okay, which doesn't really exist, but if we had a perfect laser that traveled perfectly straight, okay, in 1 dimension, regardless of how far that laser traveled before it hit something, it shouldn't ever decrease in brightness, right? Because the energy is totally traveling in 1 direction, right? So if I shine that laser pointer at a wall really close to me compared to a wall really far away from me, it should be pretty much the same brightness when it gets from here to there to the wall or wherever, right? Because it only has to travel in 1 direction, okay? It doesn't lose any of that energy. So if things only existed in 1 dimension, there wouldn't be any decrease. Gravitational force would be the exact same because if it only existed in 1 dimension, there's nothing you could change, right? It just goes along that line, okay? Now, if we had 2 dimensions, okay, 2 dimensions, then things should spread out as a circle, right? If you have a light in the center, you should see a line of brightness going out in a circle, okay? But now we start to run into problems, because if that light is spreading out like a circle, really close, it will be relatively bright because the circle is relatively small. The further away you get from that circle, okay, notice that light now has to cover a much larger distance. Okay, if I got even further, right? Sorry, these aren't perfect. Okay, but you get the point. The circle is getting bigger and bigger and bigger. The amount of energy that the light has is now spreading over that distance. So the further away you get from the center, the less bright it's going to be because it's spreading. Okay, so in 2 dimensions, it's spreading as a circle. Okay, so you would expect to see an equation that describes the spread being something like the original brightness of the light, we'll just call it B, okay, the original brightness of the light over that circumference, right, how long that circle is. Okay, so we should get something like 2 pi r. Okay, so however far away you are from that central source, okay, should determine how bright it is. Okay, or in other words, basically we could say this is proportional to 1 over r. Okay, the further you get away, we should see a decrease in brightness, okay, of 1 over r. Okay, your brightness is directly determined by how far away you are from the circle, okay, or from the center. Okay, now that's 2 dimensions. So if we lived in a 2-dimensional world, we should expect the inverse law, right, which is just 1 over r. But we don't live in a 2-dimensional world. We live in a 3-dimensional world. Okay, so now we have an even bigger problem. So let's think about light once again. So we have just a light on the ceiling, for example. Okay, the light is going to spread, but now it has to spread 3-dimensionally. Okay, so I'm going to do my best to draw this. But if you can imagine the center, we should see circular spread and a spherical spread in this direction. Okay, if you can kind of imagine a sphere here. I'm trying to do my best. Okay, now from that center, it's spreading out spherically in all 3 dimensions. Okay, and if I go further out, I should expect a bigger sphere. Okay, and so on and so forth. Okay, and so now, if you're a certain distance away, that light has to spread across that entire sphere. Okay, and so we can think of the surface area of that sphere getting larger and larger and larger as the light goes out further and further and further. So you should expect to see an equation stating that it's the brightness determined over the surface area of the sphere, right? And if you go back to math class, you should remember that the surface area of a sphere is 4 pi r squared. Okay? Or in other words, our surface area, okay, determines the brightness, and our brightness basically is proportional to 1 over r squared. Okay? So there we go. That's where the inverse square law comes from. We live in 3 dimensions. We can't change that about our scenario. Okay? Things have to spread spherically because we live in those 3 dimensions. So anything that spreads out spherically has to obey the inverse square law because it has to cover that spherical distance the further and further away it gets, that spherical surface area. Okay? So that's where the inverse square law comes from. We live in 3 dimensions. We have to spread that energy, that force, that brightness, whatever it is, over those 3 dimensions, which gives us a spherical surface area, which gives us the inverse square law. Okay? So, if you wrap your head around this, it's a really cool idea. And that's why it's consistent throughout all of physics, because it's just a property of the geometry we live in. Okay? All right, so let's look at how we describe the inverse square law. And this is specifically just for gravitational force. Okay? So this is the inverse square law stated for gravitational force. So the gravitational force between any 2 objects, okay? This is gravitational force. Gravitational, I can spell, is proportional to. So if you've never seen this sign before, okay, it looks like a little fish. Okay, it's also close to the Greek letter alpha. It's got a slight difference. but this means proportional to. And that's in physics, that's in math, okay? Everything that you'll see, this is proportional to, okay? So the gravitational force between two objects is proportional to, okay? That means we don't know the exact value yet, but it's going to be related to the mass of the first object times the mass of the second object divided by the radius or distance between them, okay? And again, we use r, okay, because going back to kind of that spherical, think of it as a sphere, right? So it's the distance between them squared, okay? So that's our equation. Next time we'll look at the actual equation, right, that doesn't have the proportional to sign, it has the equal to sign, and talk about the big constant we get right in front of it, okay? But for right now, let's just think about in terms of ratios, proportions, okay, because it's still very powerful to think about these regardless of the actual amount, okay? So force is proportional to the mass of the first object times the mass of the second object over the distance between them squared, okay? So let's just look at an example problem. So two objects gravitationally attract each other with a force of 200 newtons. If the distance between the two objects centered is doubled, find the new force of gravity, okay? So this is how I like to think of it, okay? So we know that the force is 200 newtons, okay? And now we're changing something. We're changing the distance. We could have changed the masses. We could have changed something about this setup, okay? In this case, we've doubled the distance. So we know that we have mass 1 over mass 2 over r squared is proportional to that force, okay? Now, I'm not changing anything about the masses in this problem, so I'm just going to treat all this stuff on top as 1, okay? Because it hasn't changed. We don't have to worry about it, okay? I am going to change the distance between them. So now I've doubled that radius, okay? So I'm going to put a 2 here. Well, 1 over 2 squared is the same as 1 over 4, okay? So now all that stuff on the right side became 1/4, okay? So basically what I said is whatever force I had, I now have 1/4 of it, okay? So basically I'm just going to take this newtons divided by 4, and that gives me the new force is 50 newtons, okay? So it takes a little bit of thinking because we're used to getting exact numbers and having equations. So you have to think about what's changing, what isn't changing, how's that going to affect the overall results. Okay? All right, let's try another one. So same equation. Okay, two objects gravitationally attract each other with a force of 320 newtons. The distance between the two object centers is quadruple. Find the new force of gravity. Okay, well, same thing. We know the force is 320 newtons. And it's going to be proportional to that stuff we wrote before. Okay, m1, m2 over r squared. The masses aren't changing. Okay, so I'm just going to replace them with a 1. The radius just quadrupled, which gives us a 4 here. Quadrupled means 4 times as much. So we're going to replace this with 4. 1 over 4 squared is the exact same as 1 over 16. Okay. So all that stuff on the right side became a 1 over 16. So whatever force I get, I should just divide it by 16. Okay. And that will give me 20 newtons. Okay. So if you think about this, I had 320 newtons force between these two objects. I just quadrupled their distance. Now that went all the way down to 20 newtons. Okay. Which is pretty crazy, right? Just that small amount of change totally destroyed the amount of force between them, okay? Because it's 1/16 the force just by quadrupling the distance, which is pretty crazy, okay? But really powerful if we understand it. Okay, let's do one more. Again, these aren't really long problems. They're just kind of unique problems we haven't done before. So now we have two objects. The force is 75 newtons. The distance between the two object centers is halved now, okay? So the force is 75 newtons, okay? All that stuff on the left side or right side is m1, m2 over r squared. M1 and M2 aren't changing, so we'll just replace them with a 1. R squared is now a half, so we got to be careful here. So R changed by a half, so I'm going to write it like this. 1/2 squared. Okay. Now you got to think back to fraction math. Okay. Dividing by a fraction is the same as timesing by the inverse of that fraction. Okay. So this fraction turns to 1/4. Okay, like we've seen before. But 1 over 1/4 is the same as just timesing by 4 over 1. So 1 over 1/4 becomes just 4. Okay, so all that stuff on the right side became 4. So just to be clear, let me write that again really quick. So 1 over 1/4 is the same as 1 times the inverse, or 4 over 1, okay, which gives us 4. Okay, so all that stuff on the right side became 4. That means we just take whatever force we have, times it by 4, which gives us 300 newtons. Okay, so if I have the distance, I get 4 times as much force between these two objects. Okay? All right, let's do one more problem. Again, just kind of seeing scenarios, and then hopefully this will help you get this down. Okay, so two objects gravitationally attract each other with a force of 60 newtons. The mass of one object is tripled. Find the force of the new force of gravity. Okay, so F equals 60 newtons. Now, all that stuff on the right side was M1, M2 over R squared. Now we're not changing anything about R. The distance stays the same, so we can replace this with 1. One of the masses isn't changing. Let's just say M2 isn't changing, so we'll replace that with 1. So that's just times 1. And now M1 is tripled, so that's times 3. Okay? So we have 3 times 1 over 1. Well, that all just breaks down to 3, okay? Which just means we have 3 times as much force, which makes sense. We're directly related, so if we triple the mass, we should get triple the force. Okay, so we just take 60 newtons, times it by 3, we should get that the new force is 180 newtons. Okay? But there we go. All right, so a lot of things to think about. And again, thinking about proportional problems is, again, a new skill. You may have never done it before, but it becomes really helpful, especially on multiple choice questions. You'll find that a lot of multiple choice questions in physics don't give you exact numbers. They just give you proportions. How much did this change by? How much did this change by? And that's how they had to think about physics for a long time, because they didn't have these huge calculators and super powerful calculators. They didn't have great measurement equipment. They just had to think about how things were changing. And a lot of things we wrote down back in the 1700s, 1800s in physics was just based on changes. How much is this changing by? How much is this growing? Okay, so a very important skill to have. Okay, but hopefully that all made sense. The inverse square law is going to apply in a whole lot of stuff, so make sure you do this homework. And let me know if you have any questions, and thank you for watching.